So in this lecture, we are going to study the second optimization in the KAIST compiler, which is register promotion or SSA transformation. So it is the corresponding optimization. This is the optimization that is corresponding to what is called mem to reg in LLVM, which is basically transforming memory location into registers. But before diving into the details, I'm going to say I'm sorry to upload this video late because my wife has delivered our second child, who is a girl, and yeah, so I'm now a daddy of two daughters. So going back to the main topic of this video, the first thing to do is issuing the homework 4, register promotion, and which is implementing such a SSA transformation or register promotion. Then the motivation of this optimization is that earlier than we implemented so far is producing too many memory allocations. So every variable is translated into a memory location, even though it doesn't need to be. Even though a location, C location is only used as the target of the load and store, it is stored in the memory instead of register, which is very wasteful. So the purpose of this register promotion optimization is reducing the number of such local memory locations by promoting or converting memory locations into registers. The challenge here is that we need to ensure the SSA properties we discussed in the previous lecture. So memory locations don't need to satisfy the SSA property. But on the other hand, the registers need to ensure that they satisfy the SSA properties. So the main challenge here is ensuring the SSA properties when we convert or promote memory locations into registers. So not all memory locations are naively or simply translated into registers, because there sometimes you need to define, there can be multiple stores of a single location inside a single function. So when it is the case, we need to insert a few more variables, which is in the form of finals, and by doing so, we can reassure that the registers together, the original registers and the inserted finals all together satisfy this SSA property. So this, and this transformation is also called SSA transformation because it is effectively transforming a location that is not conforming to SSA into a location, a register location that is conforming to the SSA property. You can easily test your implementation by typing this cargo test examples mem2reg, and then some tests will be going on, and it is basically checking if your implementation of the optimization produces the expected output for a given input. So the input-output files are written in this examples mem2reg directory. So you can look into those folders and the files and what's going on there. What's expected from the optimization, that is all written in this input and output files of this optimization. As always, you should submit your implementation to gg.kaist.kr, but I didn't implement the submission logic yet, so please wait for a little bit more for the submission side to be open. So let's look at how to promote memory into a register. We are going to look at a simple example first and get the general idea first, and then move on to more complex and complicated examples that involves much more corner cases of these SSA properties. So the first simple example here is converting memory locations into registers inside a single block. There is no control flows involved in this example. There is only one block, which is consisting of 8 instructions. It is quite large, but it doesn't matter. It is just executed one by one. So there is no very complicated control flow here. So here we are at the beginning of this block. This left side, and let's say this left-hand side is the original program, and the right-hand side is the expected output of the register promotion optimization. So in the left-hand side, at the beginning of the block, we are going to store the value 42 into the location x. So let's say x is the pointer to an integer, basically, which is a local variable that was declared so far. So in this example, I intentionally omitted some type annotations that was expected in the IR for simplicity and presentational purposes. But in the full IR, every value, as you know, every value is annotated with types to make explicit the type of each component of this IR. But here we omitted a few of them. So anyway, at the beginning of this block, 42 is stored to x here. X is a pointer to integer, which is a local variable. And then in the next instruction, it is loaded. And the load result is stored in this register, the I1 here. And it is used to call a function that is called sync. So sync is just a function that is sending a value to another function without doing anything. So we use this function in order to see whether the optimization actually are kicking in as we expected. So if this value is replaced with 42, then the optimization is kicking in as we expected, because we store a value 42 and we load it and then use it. And it should be the case that the loaded value here should be 42 here. So we are replacing the result of this load into 42. Similarly, in the next instructions, we are going to store 37 and load it and use it as the argument of the function call. And again, we expect this argument to be replaced with the stored value here, 37. And furthermore, even though the load instruction and the use of this load result is far away, so the first load is executed at I1, and we are using it at I6, and it is far away, and there is a store and load, other stores and other loads in between. But it doesn't matter. Even though they are far away, the loaded value should be replaced with 42 here. Similarly, the loaded value here at I4, the first instruction in the block, should be replaced with 37 at I7 later. So to summarize, we in the translation here, we are tracking which values are stored and which values are loaded from the location, and replaces the load result with the most recently stored value here. So at this point of time, at I1, the most recently stored value is 42, and as a result, this I1 should be replaced with 42. I1 is replaced with 42, and here I1 is replaced with 42 at I6. Similarly, at this line, I3, the most recent value is updated to 37, and it is replacing the load result of the next instruction. So I4 is replaced with 37. This I4 is replaced with 37, and this I4 is replaced with 37 here. So that's basically what's going on in this optimization, in this mem2reg optimization, especially for a single block. So the key idea of this optimization is deducing the most recently stored value by scanning through the block and scanning through the old instructions and replacing the load results with the most recently or latest stored value. Yeah, that's basically the algorithm. So there's nothing that changes too much, even if the multiple blocks are involved in this optimization. So here's an example again with load and stores to the variable, the pointer to the variable x here. And here, the algorithms are almost the same. We are scanning through each block. And here we can see that the most recently stored value is 42. And here it is loaded. So as a result, B0's block zeros first instruction should be 42 here. So we are replacing all occurrences of this B0 colon I1 with 42. This is replaced with this, and this is replaced with this. But the difference from the previous example is that the replaced argument here, or replaced value here, is in the different block. This is in block B2, for example. It is very much okay. So because we are replacing the load results with the most recent value in all blocks, rather than replacing the values only inside the same block, we are replacing the values in all blocks. That is basically a simple generalization of the algorithms we described so far. So this is sound thanks to the SSA property here. So this B0I1 is the name of the register that is defined only here, and this register can never be defined elsewhere. So you can see that once this load instruction is executed, the value of this B0I1 should never change afterwards. So that's the reason why at this point of time at B2 or at a very later block inside the same function, the value of this B0I1 should remain to be 42. It can never be changed, so its value should be 42 always afterwards. So that's the reason why we can replace just B0 colon I1 with 42 in the entire function in all blocks without worrying about the interferences of other codes. So similarly, so after scanning this block, we can know that B0I1 should be replaced with 42. And after scanning this block, we can see that, oh, this B1's I1 should be replaced with 37. So we do so. We actually replace those occurrences by actual values that were stored in the locations. That's basically the algorithm of this mem2resh in multiple blocks. And furthermore, we are changing the storing instruction into just null because the stored value is no longer used here. Even though it is loaded here and it is unchanged in the optimization, this loaded value is no longer used in the entire function in the result of this optimization. So as a result, we can just safely replace the store instruction by null. The value that is stored in the location X is changed, but it doesn't matter because its load result is not used at all. Instead, the load results are replaced with the actual values 42 or 37 here. So that's the reason why we can just safely replace out the store instructions, and as a placeholder, we can put just null. Okay, this is a little bit more complicated example, but it is not the full story of this mem2resh optimization. So what is interesting about this optimization is when the control flow is involved. So let's look at this example, which is basically a for loop here. So in this example, in the initial block, we're going to store the value 42 to the location x. So the initial value that is stored in the location is 42. And immediately, we are going to jump to the next block, whose name is B1. And in the B1, in the original program, before optimization, the first thing to do is loading the value from the location. So in the first iteration, this tx1 should be 42 because it was just stored here. And we add 1 to this tx1 and get tx2. And in the first iteration, the value of this tx2 should be 47 because it is 42 plus 1. I mean, it is 43. 43 is 42 plus 1. And at this line, we are going to store the value tx2 into x. And as a result, x becomes 43 in the first iteration. And lastly, we are going to go back to the top of the block here. And this is basically the loop body. And this is executed indefinitely. So in the second iteration, you're going to load it. And its value should be 43. That was stored in the next instruction. And you are going to calculate tx2, which is 44. And 44 is stored in the x. And you're going to go back to the beginning of the block. And you're going to calculate 44 plus 1, 45. And 45 is stored. And in the next iteration, 46 is stored, 47 is stored, and 48 is stored, and going on and on and on. So basically, this program is storing 42 at the beginning, and in this loop body, in each iteration, it is storing 43, 44, 45, 46, and on and on and on. So it is storing, it is incrementing the value stored in the location, basically. The interesting part of this memory range optimization is that we want to optimize out this memory location because it is just being incremented. So we are just loading from and storing to this location, and it doesn't need to be stored in the memory location. You can just store it in the register and use operations. Use write and read to these registers instead. So we want to convert this memory location into registers, but the problem is that at the beginning of this B1, it is unclear which value is stored in this X. So at the initial iteration, it is 42 definitely, but at the later optimizations, at the later iterations, the value should be tx2, which is just calculated here. So the value that is stored in the location x depend on the control flow, the predecessor of the execution. So we need to somehow express this idea. The value that is stored in x depend on the predecessor of this predecessor in the execution or counterflow in the execution. So that idea is nicely captured by this phi node here. So this phi node means that the value you are going to define a register tx0 here, and its value should be either 42 or tx2 depending on the control flow. So if you just enter this block from B0, if you just jump from B0 to B1 as the first iteration of this block, then the tx0 should be 42. Otherwise, if you are looping again and you just jumped from B1 to itself, then the value of this tx0 should be tx2. That is defined in the previous iterations line here. So by using this phi node, we can still guarantee this invariant that the x stores the value that is in the tx0 here. So when you just load from x, then the value should be tx0. That is the invariant that should be maintained by the memory edge optimization, and it is still so in the presence of this loop iterations. So thanks to these finals. So let's see how this can be obtained from this code here. So here at the beginning of this B0, we store 42 x. So we can see that at the end of this B0, the value of x, the value stored in x should be 42. So as a result, when we create a phi node, we can insert this 42 into here. On the other hand, at the end of this B1, the value stored in x should be tx2 here, because we just stored the value to x here in this line. As a result, we can easily put this tx2 here in the argument of the phi node, because it is the last value that were stored in x in this block B1. So this tx0 then is the first value that is stored in this x at the beginning of this B1. So this is such an invariant. And next time, tx1 is loaded from x, and we can see that as an invariant, tx1 should be the same with tx0 here. And as a result, this tx1 used at the next line is replaced with this tx0, which is the result of this phi node. And the store instructions are becoming null because the stores are no longer relevant in the execution of this program. So it is almost the same with the previous example, except that a phi node is inserted, and it is and the motivation behind this phi node insertion is maintaining the invariant here. When you load from x, then the value should be some register. At this point of time, this is tx0 here. Okay, this is a nice example, and it captures quite nicely about the motivation behind the phi node. But what is still unclear about this optimization is that how to implement such a translation. So this is a very simple case. This is a very simple loop, and you're just iterating a block without any nested blocks. Without any nested loops or any complex control flows depending on the value of something. It is just a simple loop. It is iterating as a counter. But if the given program is a little bit more difficult and a little bit more complicated, how to apply the memory edge optimization to such a complicated and a little bit complex loop structure and control flow structures? So that is basically the question. So more precisely, I have two challenges that I can imagine. The first challenge here, or the first question here, is that where should we insert phi nodes? So in the previous loop example, it is very clear and very easy to see that the phi node should be inserted at the head of the loop, which is at the beginning of B1, basically. But when the control flow is becoming a little bit more complicated, it is a little bit difficult to see, or we haven't studied where to insert these phi nodes. So we need to somehow generalize the notion of loop head as places to insert the phi nodes. So we need to somehow some refined notion of a loop head instead of just real loop heads. The second question, or the second challenge to address, is that which values should be inserted as phi nodes? So in the previous loop example, T42 and TX2 are used because they are the last values of the predecessors of the control flows. It is easy for such cases. You can see that it is just the most recently stored value or the last value. But what if you have the program that has a little bit more difficult control flow structures? So how to deduce what is the most recently stored values. So we need to somehow answer this question by finding a little bit more generalized invariant for such a last value. So we need to somehow capture the idea of loop hat and last value into a very well organized idea of, very organized concept of control flow graphs. So in the remaining of this lecture, I'm going to discuss the solution of the questions raised here, where to insert finals and which values to insert at the finals. So the first question, where to insert the finals? The solution to this question is related to what is called dominations or dominance frontier. So it is a little bit deep concept relating to control flow graphs. So I'm going to give you some preliminaries for the notions, for such notions. What is domination and what is dominance frontier? So here, the observation of the IR is that for every register, let's say it is %v, its definition where this v is defined is always dominating all its uses. Or in other words, you can, as an invariant, we know that whenever v is used as an argument or as an operand of an instruction, you can see that any pass from the initial block to the use point, for any such a pass from the initial block, for example, here in C, to the use of such a V, let's say D, in any pass from C to D here, or even, there are two passes from C to D, here and here. And whenever V is used here, and for any pass from C to D, you can see that the value V is defined in between, in the pass from C to D. So it is the invariant of the IR. If V is used here, then we have to guarantee that the V is defined either in D as an only instruction, or it should be defined as C as a definition of this variable V. So it is never the case that V is defined at F and it is used here. The reason is that maybe it is the case that the path is flowing from, the control flow is flowing from C to B to D. And if it is the case, V is not defined in between. So the use of this V is very unsafe. It is invalid. You cannot use V in D if the V is defined here in F. So such a property is always guaranteed by the IR of KCC, not only KCC but also GCC and LVM. So that's a part of the SSA property. As part of the SSA property, you have to see that whenever, for example, whenever V is used in D, then it should be either defined at D or C. It can never be defined at line F or E or B or A. So as a concept, it is describing what is called domination. So domination means that X dominates Y means any path from the initial block to Y has X in between. So C is the initial block here. So you can see that C dominates D because any path from C to D has C in between. C, A, F, D, it has C. C, B, D, the path also has C. However, F doesn't dominate F because there is a path C, B, D that is from the initial block to D that doesn't have F in between. And C dominates D, but F doesn't dominate D, A doesn't dominate D, B doesn't dominate D, E doesn't dominate D. A dominates F because all paths from the initial block C to F has A in between because F can reach only by A, but B doesn't dominate F because there is a path from C to F, CAF, that doesn't visit B. So using this word, domination, we can say that all register definitions should dominate all its uses. Whenever V is used at D, then its definition should dominate D, and as a result, it is either in block C or in block D. That's basically the definition of this domination and the motivation behind this domination. So as a part of this SSA property, you need to OIR guarantees this, or a register definition should dominate all its uses. So here's a little bit more example here. So we can discuss the domination between blocks, but we can also discuss the domination between instructions, because you can think of a block as the list of instructions, and each of instruction is a micro block inside this block here. So an example here is that, this is a typo here. A1 dominates A2, F, and this is a big typo here, so this is wrong here. A1 dominates A2 and F, but not the other blocks here. On the other end, B2 dominates E, but no other blocks, because D can be reached. For example, D can be reached from C by visiting A, F, D. But E is dominated by B2 because all passes from C to E, for example, C, B, E, visits B2 in between. C dominates every other blocks because this is the initial block. So any pass from C to another block should visit C in between. And D, E, F doesn't dominate anything. So that's basically the notion of domination. So using this idea of domination, we are going to deduce where to put the finals in during the map thread optimization. So we are going to insert a final whenever whenever the stores are no longer dominating such a block. So this wherever no longer dominated is conceptualized as dominance frontier, which is exemplified here. So let's say this is an A2, and the dominance frontier of this A2 is D, because from A2, F is dominated, but D is just becoming undominated by A2. So that's the reason why D is at the dominance frontier of A2. On the other hand, dominance frontier of B2 is D, because from B2, E is dominated, but D is no longer dominated. So it is at the frontier of domination. B2 is dominated, but D is not dominated. That's the reason why between this edge here, B2 is dominated, and D is in the dominance frontier. It is the frontier of the domination. It is just becoming undominated by B2. That's the reason why it is called dominance frontier of B2. The dominance frontier of C is the empty set because everywhere is dominated by C, so there is no such a frontier of domination. Dominance frontier of D is C because there is an edge from C, D to C, and C is not dominated by D. So D is itself, so it is not. It can never be a frontier of domination, but C is just becoming undominated by D. So that's the reason why C is at the dominance frontier of D. And we can also think of the dominance frontiers of multiple locations here. This is basically the union of dominance frontier of A2 and B2. And in this case, this is just D here, because D is in the dominance frontier of A2, and it is also at the dominance frontier of B2, and there is no other dominance frontier of A2 and B2. So you can think of it. You can think of it like this. So A2 is becoming A2 dominates F, but it is just D is between this edge, F is dominated, but D is just undominated. From the viewpoint of B2, B2 is itself, but D is just becoming undominated from B2. So that's the reason why D is at the dominance frontier of A2 and B2. So this very idea of dominance frontier, which is basically conceptualizing wherever it is just becoming no longer dominated. So this is used when we determine where to put finals inside in the mem-to-reg optimization. So here is basically the algorithm here. Let's say S is the set of stores set of the stores to a location that is promoted in the mem-to-reg, and the final should be inserted at such locations. It should be inserted at the dominance frontier of S and dominance frontier of dominance frontier of S, and blah blah blah. So here's the high-level idea here. So S are stores, right? And DFS, for example, D is and the stores that is in the A2 and B2, these values cannot be used as okay. Let me say in this way. At each line of the code, we need to deduce the invariant that, which value should be stored inside the location, right? And at this A2, we just store the value. So we can be quite sure about the invariant. The value of X should be some value. Also, at B2, we are equivalently confident about the invariant. Some value, this value should be stored in X here. And also at F, we can be sure about the stored value because it is dominated by this A2. And at this point of time, in the block F, the value, the stored value should be one that is stored in this A2. But at the beginning of this D, the story becomes a little bit more complicated. Depending on the control flows, the value stored in the X are different. If the control flows from this F, then the value should be one stored at this line, A2. And if the control flows from this B to D, then the value stored in X should be the one stored at here at B2. So that's the reason why we need to put a phi node here at D, which decides, which stores the value stored in the promoted memory location. Depending on the control flows, it should either be the one stored at A2 or one stored at B2. So this dominance frontier is exactly capturing this idea. This store is no longer confident at D. So this A2 value is confident at F. In F, the value stored in the location should be A2. But just when you just jump to D, you're no longer sure about that, because it is possible that the control flows from the other direction. Conversely, from the viewpoint of this B2, when you jump to D, you are no longer confident of about the stored value, because the control flow may flows from the other direction, and it is no longer the case that the stored value should be B2. So we are going to insert a phi node that is determined depending on the control flows, but that still maintains the invariant that the stored value should be equivalent to the phi node register value. So we are going to insert such a phi node here. And furthermore, we are going to insert a phi node as C here as well. And the reason is that here the same thing happens. The value stored in X depend on the control flow. If it is jumping from this, then if the value is coming from this. And if this is jumping from this, D, if the control flows from D to C, then the value stored at X is coming from this. So depending on the control flow, the value stored at X differs. So you need to insert a phi node that captures this idea. So the phi nodes should be inserted not only at the immediate dominance frontier, but also at the nested, the iterative dominance frontier as well. So dominance frontier of S should be inserted with phi nodes, and the dominance frontier of S should also be inserted with phi node, and so on and so on. So this is basically a fixed point of these iterative processes. So if a block is inside any of this set, then the block should be inserted with the phi node. So here's an example. If A2 and B2 are stores, and then the phi node should be inserted at D and C as a result of this algorithm. So this is the high-level idea, but we still didn't discuss how to compute the domination relation and dominance frontier. That will be discussed in a later video. And let's move on to the second question, which is which value should be stored in the phi node. So it is easier than the question one because we already have quite a lot of ideas how to do it. So again, let's say that A2 and B2 are stores, and we are going to insert a phi nodes at C and D. And let's say that the values stored at A2 and B2 are VA and VB. And the phi nodes inserted at C and D are, let's say they are phi C and phi D. Oh, this is a typo. This should be phi D. And the first thing to do is that for each block, we are going to deduce the initial and final values for each block. So let's start from the initial block C here. So initial block C, the initial value stored at the location X should be phi C, because a phi node is inserted and it is meant to have the value stored in the location. So we know that when you load a value from X, then it should be the same with this phi C. And the final value is also a phi C because there's no store inside this block C. So the initial value should be preserved at the end of the block. So final value of this value should also be phi C. And now the initial value of at the beginning of this A should be phi C because this final value stored in the location as C is phi C, and it should be preserved. When you jump from C to A, the value stored in the location is preserved, and as a result, the initial value at the block A should be phi C as well. But something is different for the final value. The final value stored in the location at A should be VA, because A2 stores VA to the location. So find this. You can see that the final value should be VA. Similarly, the initial value of block B should be phi C because you jump from C to B. On the other hand, the final value should be VB because inside this block, B2 stores the value VB to the location here. And similarly, the initial value of F should be VA and the final value of F should be VA because the value is inherited from the parent A and it is not changed because there's no store to the location. And almost the same thing happens for E as well. The initial and final values stored in the location should be just VB. And in the last block D, the initial value is phi D because a phi node is inserted and it is meant to be having the value stored in the location. And the final value is also phi D because there's no store inside this block D. Okay, so in this way, we deduce the initial and final values for each block. And as a next step, we are going to see which value should be inserted in the finals. So let's say that this phi D, which is inserted at this block, so this is having the value depending on the predecessor. If the control flows from this F to D, then the value of this phi D should be final F, which is basically VA, which we calculated here. And if the control flows from B to D, then the value of this phi D should be the final value of B, which is VA, which we calculated here. Final value of B here is VB, and the final value of F should be VA. And as a result, when we insert a phi node, phi D here, then it should be the finals of VA and VB, depending on the control flows. So you can calculate this expression directly from the initial and final values for each block of the, for the location here. So basically, this is an example, an algorithm that is working on the example. So here is a little bit more algorithmic representation of what I just described. So we are iterating through all blocks here. And we first calculate the initial value for x. And if a phi node is inserted at x, then we are going to use the phi node. Init x is, for example, phi D for the block D. Otherwise, we are going to use the final value of the closest dominator of x. So what is meant by the closest dominator is that, let's say there's an f here, and f has two dominators. One is C and one is A. But A is closest because when you're going through C to F, you're going to visit A as the latest one. So both C and A are dominating F, but in every pass from C to F, the initial block C to F, A is always later than C. So that's the reason why A is the closest dominator of F. Or in other words, it is the immediate dominator of F. So similarly, B's immediate dominator is C, and E's immediate dominator is B, and D's immediate dominator is C. So that's basically the high-level description and definition of this immediate dominator. And if the phi node is not inserted at x, then we can say that there is no need to insert such a phi node, and the initial value at the beginning of this block x should be the final value of the predecessor. Dominator, the immediate dominator of this x. So that's the reason why init x is initialized with immediate dominator of x's final value here. So the f initial value is the final value of f a, and final value the initial value of b is the final value of c, etc., etc. And later we scan through the block, and if you meet the store, then you update the current value, which is initially x, initially init x, and it is updated when you meet the store instruction. And at loads, you're going to replace the load result with the current value. So that is already dealt with the previous example with a single block. The first example already has the idea of this algorithm here. And after scanning through all the instructions inside the block, you are storing the last value, the last current value inside this final x variable. And at the later stage of this algorithm, we are going to use this final x as the value that should be inserted in the finals. So if for example, when you insert the final node of D here, and these predecessors are f and b, and you're going to use the final values of this f and b when you insert the final node at this D here. So phi D should have a final value of f, which is a predecessor of D, and the final value of b, which is also another predecessor of this D. And as a result, this phi D it should be either VA or VB, depending on the control flow. So this is basically a algorithmic representation of this idea, and which is the what's going on to how to deduce the stored value at each line as an invariant, as a generalized invariant of used in this mem-to-age optimization. One important thing to notice that, so you're basically iterating through all blocks here. So we're going to do scan x, C, A, F, D, B, E for every blocks. So you have to scan through all the blocks here. But the important thing to do is that you should iterate these blocks in a specific order. So you have to use what is called reverse post order, which has a very nice property here. If x dominates y, then x is ordered before y in this reverse post order. So for example, C is dominating everything. So C is at the beginning of this reverse post order. And similarly, A is dominating F, and as a result, A is ordered before F in this reverse post order. So that is the property we need to have in this algorithm, because here we are using the final value of a dominator of x as the initial value, and in order to do so, we should have already processed the dominator, the immediate dominator of this x, and that's the reason why we are calculating this in a reverse post order, which satisfies this property. Since idom x is dominating x, f is already calculated. As a result, init x is properly initialized. So here is the remaining details of the algorithms, which will be discussed in a later lecture. And the first thing to discuss is that, okay, how to promote multiple location at once. So if you see the examples IR in the KCC repository, you can see that multiple locations are simultaneously promoted. And my advice is that it is not that difficult. You can just process all the locations at the same time. But I recommend you to implement the mem-to-age for a single location and then generalize it to multiple locations. So this generalization is not that difficult. So you can just adjust some variables and use some hash tables or something like that. And I only mentioned the reverse post order RPO here, but I didn't introduce how to properly traverse the graph in this reverse post order so that we can have this property. So you can just Google reverse post order, and there are multiple articles, quite good articles on the algorithmic details of this reverse post order, and you can read any article. And I think a more important question is why this property is holding. Why, if x dominates y, then x is ordered before y in a reverse post order. So you can think of it in home, and as a result, it is a homework. So I'm not going to open gg.kaist.ac.kr entry for this homework, but I strongly recommend you to think on it at the home. And the final remaining details on this algorithm is how to calculate the domination relation and dominance frontier. So we are going to discuss this topic in the next video based on the three observations here. So you don't need to understand everything of this, every line of this, but we are going to use this as a starting point of the implementation of this domination relation and dominance frontier algorithms. So this is pretty much everything about today's video. So today we discussed the motivation of the mem-to-reg optimization, which is converting memory locations into the registers. And this is quite beneficial because IRGen produces a bunch of memory locations even when it is unnecessary. And registers are more easy to deal with in the optimization. So later we are going to apply other optimizations like global value numbering, which is working on the registers and deduce the duplications of the computations and shrink it. And when doing so, this mem-to-reg is, the registers will play a key role in the later optimizations. That's the reason why we are performing this mem-to-reg optimization here. And also we discussed the algorithms of this mem-to-reg quite briefly. So we discussed the key ideas of these mem-to-reg and the key challenges of this mem-to-reg optimizations. So these are all about finals, basically. How to insert finals properly, where to insert, and which value to insert. So these are two key questions about the finals in the mem-to-reg optimization. And that is pretty much everything. And in my opinion, this SSA transformation and mem-to-reg is the most beautiful concept in the study of the programming languages. So this SSA transformation paper is my favorite paper by far, and I am very admiring this work because it is very nice and it is very not only beautiful, it is also impactful in the real world. So after this algorithm is discovered, every major compiler is adopting this idea, and now GCC and LVM and other major compilers are all using SSA as their internal IR's style. So I hope you are going to enjoy this and enjoy implementing the optimization.